In this lesson, we're going to discuss power in a parallel resistive circuit. We'll calculate the power dissipated by each branch and the total power of the circuit. During the lesson, I won't stop and refer you to your TVI guide. However, when you see this in the upper left-hand part of your screen, go ahead and complete that particular TVI guide item. Since you're already familiar with electrical power in a series circuit, you should recall that power is the product of the voltage E and the current I in a circuit. Power in a parallel resistive circuit is dealt with in the same manner as in the series circuit. However, there's one major difference. In a series circuit, there's only one path for current. So, the same current is used to determine the power throughout the circuit. In a parallel circuit, there's always more than one path for current. This means that the current through a given resistive branch is used to determine the power dissipated by that particular branch. The sum of the branch currents, IT, is then used to determine total power. To illustrate this, let's use this circuit. We have a DC power source and switches that allow us to switch the branches in or out as we wish. With the switches closed, resistors 1, 2, and 3 are connected in parallel across the power source. Meters 1, 2, and 3 are used to indicate the current through the individual branches, while meter 4 indicates total current. With this switch closed and the other two open, let's determine the power dissipated by branch 1. R1 is a 30 ohm resistor. Meter 1 indicates 1 ampere of current. Since we know the ohmic value of the resistor, the current flow through the resistor, and the voltage across the resistor, we're free to use either of the power formulas to determine the power for branch 1. Let's use the I squared times resistance formula. Looking at meter 1, we find that the current is 1 ampere. The value of R1 is 30 ohms. Applying these values to our formula, we have 1 times 30, which gives a power of 30 watts dissipated by branch 1. Let's notice that with only one resistor connected, meter 1 and meter 4 indicate the same value. But watch what happens when branch 2 is added to the circuit. The reading on meter 4 has increased. This is because we have added an additional path for current in the circuit. Keep this in mind. With this branch in the circuit, let's now determine the power dissipated by resistor 2. Again, we have the necessary facts, so we can use the power formula we choose. For branch 2, let's use the E squared divided by R formula. Across the circuit, we have 30 volts. The resistance of branch 2 is 15 ohms. Substituting these values into the formula, we have 900 divided by 15, which gives 60 watts of power dissipated by branch 2. Observe meter 4 once again, and let's add branch 3. Again, the reading on meter 4 has increased. With branch 3 now in the circuit, let's determine the power dissipated by this branch. This time, let's use the voltage times current formula. Once again, the applied voltage is 30 volts. Meter 3 indicates 3 amps of current flowing in branch 3. Using these values in our formula, we have 30 volts times 3 amps, or 90 watts of power dissipated by branch 3. We've determined the power dissipated by the individual branches. But how can we find the total power dissipated? In a parallel circuit, total power is equal to the sum of the power of the individual branches. In this circuit, then, we simply add the power dissipated by all 3 branches. So let's see. We have 30 watts for branch 1, plus 60 watts for branch 2, plus 90 watts for branch 3. This gives us 180 watts of total power dissipated by the circuit. Stated in a formula, we would have total power is equal to power 1 plus power 2 plus power 3. We also know that in a parallel circuit, total power is equal to the product of the applied voltage and total current. In this circuit, meter 4 indicates that total current is 6 amps. The applied voltage is 30 volts. Substituting these values into the formula, we have 30 volts times 6 amps, or again 180 watts of total dissipated power. Recall that we started determining the power dissipated with only one resistor in the circuit. As we added another branch, the total power dissipated by the circuit increased. From this, we can conclude that as parallel branches are added to a parallel circuit, total power dissipated increases. Recall also that each time we added a branch, the total current increased, while the voltage was the same in all cases. This can mean only one thing. Total resistance decreases as more parallel branches are added. If we know the total or equivalent resistance of the branches, we have another way to solve for total power. We can find the equivalent resistance by dividing the applied voltage by the total current. EA is 30 volts, and meter 4 indicated that the total current was 6 amperes. Applying these values to the formula, we have 30 volts divided by 6 amps, or a total or equivalent resistance of 5 ohms. By using the equivalent resistance and the total current, which was 6 amps, we can now proceed to solve for total power. Total power is equal to the total current squared times the equivalent resistance. Substituting 6 amps and 5 ohms and solving, total power is again equal to 180 watts. Let's see what we've learned about DC power in a parallel resistive circuit. 1, we found that in any circuit, power is the product of voltage and current. Second, we found that there's always more than one path for current in a parallel circuit. We found that each branch current is used to determine the power dissipated by that particular branch. We saw that total power is equal to the sum of the power of the individual branches. Remember, there are several formulas that can be used to determine power. All you have to do is analyze the given values in a circuit and select the proper formula for those values. Soon you'll be determining power in more complex circuits. So keep the things in mind that you've learned in this lesson. They'll be a big help to you. I'll see you again soon.